Allora, Alessandro Giachino is a postdoc in Krakow, and he will give us the last hour of exercise for regarding the Maiani lessons. He will cover topics that are complementary to those covered by Pilloni. Okay, so please, Alessandro, you can start.
Yes, thank you very much for the invitation and good morning to everybody. So in the lesson by Professor Maiani, you have learned that hadrons can be classified into SU3 flavor multiplets, right? So you have learned that ground state Q-bar mesons can be classified into an SU3 flavor nonet with spin 0 and an SU3 flavor nonet with spin 1, while the baryons can be classified in a SU3 flavor octet with the total spin 1 alpha and an SU3 flavor decuplet with the total spin 3 alpha. And this classification comes just from symmetry principles, right? So for example, in baryons, we have two constraints. One constraint, which is the Pauli principle that the three light quarks must satisfy. So overall anti-symmetrization of the three quarks. And the second constraint is that due to confinement, hadrons happen to appear just in color singlet. Hadrons are colorless. Okay, and but in order to build these multiplets, one has to be able to calculate the tensor product between the fundamental representation of the SU2 spin, SU3 flavor, and SU3 color. So with Alessandro Pilloni, you have learned how to calculate these tensor products with the graphical technique, let's say, which is beautiful, but also can be, of course, unfeasible if the dimension of the representation that you are calculating is too big. For example, it's not common to do calculations in this way among the physicists which work within group theory. And in this session, I want to show you a more powerful technique to perform with calculation, which is called the Young tableau technique. Tableau, okay, technique. And in the second part of the lessons, if we have enough time, I would like to calculate the proton wave function with the help of the Young tableau technique from scratch. So let's start from the Young tableau technique. The great advantage of this technique is twofold. First, the pattern is universal. Which means that it holds for every SUN, SU2 spin, SU3 flavor, and so on and so forth. And then second, that any diagram with n boxes defines a given symmetry class. I will explain in more detail later, but this means that at the same time, you are able to know the multiplet, which the baryon, the hadron in general belong to, and also the symmetry property of that multiplet.
Sorry. The pattern work also for any subgroup of GL or only for SU?
You are asking if the pattern works also for any subgroup of any SUN?
No, of any GL, general linear group, or only for SUN?
It works both for SUN and for the permutation group SN. I don't know that the other group you are speaking about.
Okay. Thanks.
Okay, so let's dive now into the mathematical details. First, I have to list some rules in order to make the calculations. The first rule is that any fundamental representation of SUN can be represented in the language of Young tableau technique with a box. So we denote the fundamental representation of SUN like a box. Then a Young tableau diagram is a left justified diagram, a standard Young tableau diagram. Which means that any row must not be longer than the row on top of it. So for example, this diagram like that is not allowed, is not a standard Young tableau, because you see that the second row is longer than the first one. This is not allowed. Okay. I would like to, okay. Next. Okay. The third rule, any column cannot have more than n boxes, of course, because in SUN, for a column with n boxes, can be crossed out the singlet. So again, some examples. In SU2, this is a column of 2 boxes. This is just a singlet of SU2. In SU3, a column is with the 3 boxes is the singlet of SU3. Okay. Then how can I calculate the complex conjugate of a diagram? So we arrived for 5. A complex conjugated of a diagram can be obtained by switching any column of length k with a column of length n minus k. So again, let's consider SU3. This is, first rule, the fundamental representation of SU3, and it has k equal to 1 box, which is the complex conjugate. It's given by a column with n minus k boxes. So it's given by 3 minus 1, 2, a row of 2 boxes. This is the complex conjugate. Okay. I think that we can discuss how to find the dimension of these representations. The dimension of a given representation can be obtained by the following ratio, and I'm going to define how to calculate the numerator and the denominator. So the numerator can be calculated like that. Fill the top left box with n. Then moving towards the right, write the number increased by 1 unit. And moving toward the bottom, write the number decreased by 1 unit. So, for example, take this diagram. The numerator is given like that. I put n on the top left box, then n plus 1, n plus 2, and moving towards the bottom, n minus 1, n minus 2, and the same for the other column, n minus 1, minus 1, n. Then I get the product of all the entries. So n, n plus 1, n plus 2, and so on. This will give me the numerator, okay? For the denominator, things is like that. For every box, for each box, count the number of boxes at your right side. And sum with the number of boxes on the bottom side. Plus 1, which is the box you are just considering. So in general, this is also, I show you. This is also called the hook, because if you have a diagram like that, for example, okay, here there are many, but let's consider, for example, I have to make this for each box. So You see, I have just one. Then I consider this box, one box at my right side, one box at my bottom side, 1 plus 1 plus the box that I'm considering. So the easiest way to do this in reality is just to cross in this way with the so-called hook, as you see. And the numbers of boxes crossed by the hook is the hook length. If you multiply all the hook lengths, you get the denominator. So in this case, we have 1, then we have 3, then we have this other hook, which has a length of 3, then we have this other one, which is 6, and there shouldn't be any else. Okay, then you take the ratio and you get the dimension of the representation. Of course, we will see some examples later. And then in order to make the calculations, we still need one thing. So we know that any Young tableau corresponds to a given irreducible representation of SUN. So if I take the direct product between the fundamental representation of between irreducible representation of SUN, I can decompose it as a direct sum of irreducible representation, right? And I can do this just by means of a Young tableau in this way. So consider that we are looking for in SUN the direct product between this diagram, which I call diagram number 1 for convention, and this other diagram. Okay, so first, in the second diagram, we have to fill with, let's consider, for example, labels A, B, C, okay? Fill with A the first row, and with B the second, and so on. So here we have just 2 rows. Okay, then we have to pick up one box and attach one box at a time. This is important. And in all possible ways, and also starting from A, of course, to the first diagram. What does it mean in all possible ways? Well, it means that the resulting diagram must be a standard Young tableau. So for example, I cannot have in SUN a diagram with more than n boxes, or I cannot have a diagram in which a row is longer than the row on top of it, okay? There are 2 more constraints which come from the symmetry property of the Young tableau that I think I forgot to say, but within a Young tableau, okay, I write it right now. In a Young tableau, you have symmetry in rows and anti-symmetry in columns, which means that any tensors whose indices are on the same row are completely symmetric tensors, while on the contrary, any tensors whose indices are on the same column are completely anti-symmetric tensors. Okay, so because of this, when you take the direct product of the diagrams, you cannot have more than one same label, let's say, on the same column. So you cannot have a thing like that. In SU, let's consider, for example, SU3, you cannot have a diagram like that, because you have two A in the same column. This is not allowed. Okay, then there's another rule. Reading the diagram from the right to the left, you should have the number of C, which is lesser than the number of B, which must be lesser than the number of A. So for example, consider this diagram. I start reading the diagram from the top to the bottom, as always, from the right to the left. And then what happens? That I meet B before meeting A. So this diagram is not allowed. Instead, if I have this case is allowed. And attention, this case is also allowed because I have symmetry within the row. So I can have more than one, the same symbol appearance more than once on the same row. So these two are allowed. Okay, so I think that now we have all the ingredients to make some calculation. So for example, with Pilloni, you calculate in color space, the product between 3 and anti-3, right? So which is 3 in the language of the Young tableau? Well, it is the one box. And how is the dimension of this box? How do I know that it's 3? Let's apply the rule that we have just set. So n is equal to 3, and I have just one box. What about the Hawk length? It's just 1. So the dimension of this diagram is 3. What is anti-3? Well, I have to take the complex conjugate of this diagram. And is the dimension right? Let's see. 3, 2. So numerator is 3 times 2. What is the denominator? Is 2. The Hawk length, I have just one Hawk. So the dimension of this diagram, which I denote as 1, 1, first one box in the first column, one box in the second column, which is quite a common notation in the field. The dimension of this diagram is 3. And it is the anti-3 because it's a complex conjugate of the fundamental representation. Very good. Now, let's look at the direct product, right? So what do I have to do? I have to fill the first row with A, the second row with B, and I start one box with just the first box, right? Because one at a time in all the possible, and I have to attach it to the first diagram in all the possible ways. So what do I get if I do that? Well, I get this diagram. I get also this diagram, right? And then I have still to take the direct product with B. So let's consider this one first. I attach first B to the right side and I get this pattern. Then I cannot attach B here, right? Because in that case, this pattern is not left justified, so it's not allowed. But I can attach B here. Okay? And then consider the second. In this case, I can attach B in this place, in the right top side. And I have one more possibility. I can attach B on the bottom. Are all these diagrams allowed? Well, this diagram is not allowed because you see, when I'm reading from the right to the left, I met B before meeting A. This is not allowed. What about this diagram? Well, in this case, I meet A before meeting B, so this diagram is fine. This diagram is not allowed for the same reason as the first one. And this diagram is also fine. Remember that we are working in SU3, so 3 boxes are allowed. And moreover, this diagram, if you remember the rule, one of the rules that we have just seen, these diagrams can be crossed out the singlet. So this is the SU3 singlet. Right? What about this other diagram? What is the dimension of this diagram? So I put 3 here on the, as always, on the top left side, 2, 1. So the numerator is the product of all the entries, 3 times 2 times 1. The denominator, I have to find the Hawk's length, right? So how many Hawks there are here? There is this Hawk with length 2, and there is this other Hawk. Sorry, I made a mistake. I made a mistake for the numerator because going to the right side, I have to increase the number by 1 unit. So the numerator is 3 times 4 times 5. Okay. And the denominator, we have the first Hawk of length 2, the second Hawk of length 3. So what is the dimension of this diagram? Is 5, 4, 3 divided by 2, 3. Sorry. I'm sorry. I'm very sorry. This diagram was not allowed. I have to consider this other one. Okay, the dimension is 10, but this diagram is not allowed. Okay, so let's compute the dimension of this other diagram, which is allowed.
It's better if you cancel that.
Yeah, yes.
Cancel that one because you already put the cross. That means that is not allowed.
Yeah. Previous. I think it's already canceled. Okay, so the allowed diagrams are the following two. This diagram and this diagram, right? And this is the color singlet. What about this diagram? Let's compute the dimension. So this is 3, 4, 2, numerator, right? And the denominator is, okay, in this case, I have just one hawk of length 3. So the dimension of this diagram to 1 is 2, 3, 4 divided by 3, which is 8 in color space. So what we found is that in color space, 3 times anti-3 is equal to 1 plus 8. Very good. So now let's consider in color space the following product, which was another example which was done by Pilloni, but with the graphic technique. So I'm looking for the product between the fundamental representation 3 times so let's start by considering this part. I put A here, and I have two possibilities, right? I have this possibility, and I have these possibilities. Both possibilities, as you can see, are allowed. Then I have to take the product with the last box. Okay, what about the dimension of these two? Well, the first one, 3, 4, numerator is 3 times 4. And for the denominator, I have just one hawk. So the denominator is 2. And the dimension is 6. Let's consider this other diagram. You see that I have one hawk with length 2. So the dimension of 1, 1 is 3, but we know that this is the conjugate of the fundamental representation, right? So this is the anti-triplet. And so we get, as a first result, that 3 times 3 is equal to 6 plus anti-3. Okay, now let's consider the last one. And it's better that I create another page. Six anti-3, yes, times 3. I put A here. For this diagram, I can attach A in 2 different ways. Sorry. Like that. and like that. And both are allowed. What about this diagram? I can attach A at the right side, like that. And I can also attach A at the bottom side to make the singlet. So this is the singlet. We already computed the dimension of this diagram in color space, 8. We computed the dimension of this diagram, 8. By mistake, before I computed the dimension of this diagram, you know, remember that this is 10 in color space. Okay. Are there any questions as far? Okay. Very good. Two more things regarding the rules for obtaining the irreducible representation. I forgot to say that if you get more than one diagram with the same pattern, but different, let's say, label structure, you have to keep both. You have to keep all of them. And instead, if you have more than one diagram with same pattern, and also same label structure, discard the copies, because these are just copies. You keep just one and you discard all the copies. Okay. Then, as the last exercise, I would like to show you how to calculate the proton wave function from scratch. So the proton wave function is given by the product of the isospin wave function, spin part, the color part, psi, and the orbital part, spatial part, right? So for ground state 3-quark baryon, like the proton, the spatial part is completely symmetric, okay? And the specific analytic expression of this part depends, of course, on the specific Hamiltonian that you are using in order to solve the three-body problem, right? So I cannot write it. But of course, for 3 quarks in the S wave, this is completely symmetric. The color part is completely antisymmetric, and with the correct normalization factor can be written like that. Proton is made up of 2 U quarks and 1 D quark, so it's U alpha, U beta, D gamma, where alpha, beta, and gamma run over the color indices, right? So right, green, and blue. So what about this part? So let's start by considering the isospin. You will see that the isospin and the spin part, mathematically speaking, are the same, because in one case you use SU2 isospin, which is in the other case SU2 spin, but the mathematically is the same because it's always SU2, right? So consider that we are combining two quarks in SU2. So we calculate this product, and this product is equal to this diagram if you apply the rules that we have just discussed in order to calculate the direct product between fundamental representation of SUN. You can decompose it as a sum of this diagram plus this diagram. And this diagram in SU2 crossed out the singlet. So this is the antisymmetric tensor of rank 0 in SU2, right? And we know it. This is 1 over square root of 2. Can be, of course, U and D. I cannot add UU or DD, right, within the same column. So it should be UD minus DU. And what about this one? Well, let's calculate the dimension. We are in SU2, so I have to put 2 here. I increase by 1 unit going towards the right side. Numerator is 2 times 3. The denominator is 2. So the dimension of 2 in SU2 is 3. This is the triplet. 3 states. What are these states? Well, UU, a combination of UD and DU, and DD, right? So this one is simple because this one in the isospin notation, total isospin for the component is 1, 1. And the same for this state. This is 1 minus 1 in that case. This one is more difficult to find, but okay, there are 2 ways to find this state. One possibility is to look for the orthogonal state of the singlet. And if you look at the orthogonal state of the singlet, you immediately obtain that this state must be UD plus DU. How many minutes do I have? Okay, it's almost 12. Okay. Are there any questions regarding this part? Okay. And another possibility to get this state is to use the so-called ladder operator, right? The ladder operator T plus, T minus in SU2, E plus, I minus, sorry, in SU2 are defined as I1 plus or minus I2. And this operator decrease or increase the third component of an isospin of 1 unit, right? So if apply I minus to the UU state, I prefer to write like that. This is in the isospin notation can be written like that, right? So this is, if I apply I minus to U, I get UD plus DU, right? What about this? Well, the eigenvalue of I minus over a state of total isospin E and third component I3 is I plus 1 minus I3, and then since this is minus, I have to put minus here. For the complex conjugate of I minus, which is I plus, I have to put a plus here, right? And the third component is decreased by 1 unit. Okay, so if you make these simple calculations, you get that I minus applied to the state 1, 1 is just square root of 2, 1, 0. And so we got that 1, 0 is, of course, 1 over square root of 2 ud plus du. So we have the following states. The singlet, which is 1 over square root of 2 ud minus du. The triplet with total third component of isospin 1, which is just uu. The triplet with the third component of isospin equal to 0, which is 1 over square root of 2 ud minus du. And, the triplet with the third component equal to minus 1, which is dd. Okay, now we have to combine with the third quark. For the singlet, for the total isospin equal to 0, this is simple because if I can just do like that, right? Of course, this is u because I'm looking for the proton wave function, and I have already 1u and 1d. So this is u du minus duu. So if you look at this isospin wave function, you see that if you exchange the first with the second quark, you get a minus sign. So we called it a mixed antisymmetric function, right? And what about this? So in this case, I have to multiply to combine with the d quark. And what I'm doing is I am combining a state 1, 1 with a state 1 alpha minus 1 alpha, because this is d. In that case, I have to combine with the u quark. And what I'm doing is that I'm considering the product between 1, 0 and 1 alpha plus 1 alpha, because this is u. What about this one? Well, this one does not contribute to the proton wave function, right? Because I have already 2d. So this can be contribute to the neutron or to the delta, for example. When I combine total isospin equal 1 with the total isospin equal to 1 alpha, I can get two possibilities, right? I can get a state with total isospin equal 3 alpha, and in that case, I will get the delta plus particle. Or I can get a state with total isospin equal 1 alpha, which is the one that I'm looking for. So a total isospin 1 alpha, third component 1 alpha, the proton, is given by a certain coefficient by times this state 1, 1, 1 alpha minus 1 alpha plus a coefficient b times the other combination, which is 1, 0, 1 alpha, 1 alpha. And what are these coefficients? Well, these are just the Clebsch-Gordon coefficients, right? So the Clebsch-Gordon coefficients I should have somewhere. So I'm looking for 1 alpha, 1 alpha, combining total isospin 1 with total isospin equal to 1 alpha. And this is square root of 2 over 3 for the first 1, 1, 1 minus 1 alpha, minus square root 1 over 3 for 1, 0, 1 alpha, 1 alpha, right? So square root of 2 over 3 minus square root of 1 over 3. So let's come back Okay, so this is square root of 2 over 3, and this is minus square root of 1 over 3. So this can be written like that, 1 over square root over 6, and this is just 2, 1 is UU, this is D, right? Minus 1 over square root of 2, right? 1, 0, but 1, 0 is square root of 2 UD plus DU, so I can cancel square root of 2. So this is minus UD plus DU times U, okay? So 1 over square root of 2, square root of 6, sorry, UUD, 2 UUD, minus UDU minus DUU. And you see that this has a different display, isospin function has a different permutation symmetry with respect to the first two, as is a completely symmetric with respect to exchange of the first two. So we call it key, I have to move this, okay, key MS, sorry. Okay, we almost done. Because now you know that the overall wave function must be completely anti-symmetric. So what can we do is to take, to consider both combination of isospin and spin with the proper symmetry. As I said, the spin wave function are exactly the same as the isospin wave function. And so with the correct normalization coefficient, the proton wave function will be the product between the mixed symmetry isospin part with the mix, sorry, I called the isospin part with phi, the mixed symmetry spin part plus mixed antisymmetric isospin part, mixed antisymmetric spin part. Then we have the color function that we already written at the, and sorry, I called it psi, okay, times the spatial part. Okay, and that's all. Do you have some questions now? Everyone is still alive?
That was actually very useful, so thank you.
You're welcome. I hope that you could appreciate how useful and how powerful is this technique to calculate the product of between the irreducible representation of SUN.
So Alessandro, apparently there are no further questions, so just thanks to you by many students. And okay, I also want to thank you, of course, for your nice lecture. Just if I can add a point, of course, this young tableau technique is extremely powerful, and you learn to use it in a very mechanical way, in a sense, no? And it's and you can work. Eh?
Yeah.
You said you didn't say anything, seems to me, about the way these rules are demonstrated, no, in formal group theory.
Yeah,
which is the real problem, no. So I don't know if you have you can suggest just to add a reference where the curious student or the curious teacher can find it, since you are an expert. I use it occasionally. I teach this actually to my students, but I would not know where this has been demonstrated. I have many books. I never studied this. Maybe since you are a practitioner, you can suggest something.
Yes, I know one book by Stanku, which is quite a great book. Yes, I don't remember the title. Should be quantum mechanics, group theory in quantum mechanics, something like that. Yes. And I think that this is a very great book because you can find not only, okay, the formal, all the theoretical part, right? But this you can find almost everywhere.
Yeah.
But also some practical example, which is the very interesting point for us, which are phenomenologists in particle physics. So we need to know how to calculate these things, right?
Yeah.
So I think that this is a good book.
Thank you. I will check, and in case I will ask you if I don't find it.
Oh, of course, you can write me an email, of course.
Very useful, Alessandro. Thanks.
Thank you very much.
I do not see other comments, questions. No. So,
would you just mind?
Sure.
Would you mind writing the name of the author in the chat?
Yes, the name of the author. Yes.
Thanks.
Yes, of course. Tanku. It's
I know the lady, but I don't know the book.
Yes.
Very good.